At the extreme fringe of our solar system, distant, icy bodies trace slow, highly elliptical orbits through the dark. Standard Keplerian physics maps the tightly bound inner planets with perfect precision, but those same mechanics fail to explain the synchronized clustering of Extreme Trans-Neptunian Objects, or ETNOs. These are minor planets that orbit the Sun far beyond Neptune, and their paths align in a way that standard gravity models cannot resolve. For years, astronomers have hunted for an unseen perturbative force to explain this clustering, specifically the gravitational signature of a massive, undiscovered Planet 9. This evidence suggests the entire solar system is governed by a deeper, undiscovered organizational structure. Standard gravity models describe how planets move, yet the sheer synchronization at the edge of our system implies we are missing the mathematical architecture that dictates exactly where those bodies are allowed to exist. In March 2026, Allan Christopher Beckingham published a theoretical model designed to solve this discrepancy, called the Biodal Restoration V6.2. This model maps the solar system as a phase-locked architectural lattice, discarding the concept of independent planetary tracks. The foundational axiom of this entire structure relies on a single discrete temporal interval, locking all bodies into resonance. Beckingham defines this interval as the Beckingham Metronome, explicitly stating its value as roughly 1.7062 terrestrial years. This universal cadence dictates where gravitational stability can actually occur. Much like harmonics on a vibrating string, this force requires every planet, asteroid, and undiscovered body to mathematically snap into these specific structural nodes to remain in phase. This creates an immediate physics problem. A rigid temporal metronome should break down because Earth, our observational reference frame, is constantly moving through the galaxy. This equation is the Dynamic Tau Tensor. It is the mathematical construct Beckingham uses to preserve phase stability under conformal frame shifts. The first modifier, radial velocity, accounts for our physical motion. Next, the wave speed correction term adjusts cadence based on local energy density. Finally, the denominator uses an electromagnetic coupling constant, anchoring to fundamental physics. By calculating these variables, the framework proves that the underlying 1.7062-year heartbeat remains mathematically stable, regardless of how fast or where the solar system travels. With the tensor stabilizing the math, the framework begins mapping physical bodies to the lattice. Mercury, Venus, Earth, and Mars lock into nodes 1 through 4. The sequence reaches node 5, the asteroid belt. The model identifies this region as the remnant of a high-energy fragmentation event. This formula represents the phase space exhaust term. The lattice balances the energy budget of that destruction by calculating specific orbital energy deficit against the participating mass. Earth also receives a unique structural designation outside the standard sequence. It is explicitly isolated as the observer reference frame for the system. The model recharacterizes the inner solar system. Earth functions as the observational lens, while the asteroid belt serves as a mathematical exhaust valve, stabilizing the rest of the lattice. Building the framework outward, Jupiter, Saturn, Uranus, and Neptune lock into nodes 6 through 9. The Kuiper boundary and Pluto slide into node 10, completing the known bounds of our system. However, a mismatch exists between the theory and our observations. The mathematical lattice operates on an idealized 364-day cycle, yet the observed terrestrial year is exactly 365.24 days. This diagram shows two overlapping circular timers, visualizing what the model calls temporal gauge freedom. This roughly 1.24-day residual acts as a temporal dampener. This buffer absorbs the friction between theoretical perfection and physical reality, preventing the entire phase-locked system from requiring constant orbital braking to stay aligned. The 13+1 architecture is currently empty past node 10. To physically close the energy budget, the lattice requires two massive undiscovered components. Node 11 is an intermediate Planet 9 scale perturber containing 5 to 10 Earth masses, required to mediate resonance within the Kuiper belt. Node 12 is the ultimate structural anchor, a distant brown dwarf binary companion resting roughly 63,240 astronomical units away. An astronomical unit is the distance from the Earth to the Sun. This star map plots explicit astrometric search coordinates generated by the model. Right ascension and declination act as longitude and latitude for the night sky. Node 11 is projected at right ascension 4 hours 15 minutes, declination plus 12 degrees 44 minutes. Node 12 sits at right ascension 6 hours 18 minutes, declination minus 30 degrees 15 minutes. The bimodal restoration generates highly specific search coordinates, turning a theoretical lattice into an active astronomical treasure map. The concept of a distant binary companion has precedent in mid-20th century Oort cloud models. Historical nemesis hypotheses viewed the companion as a chaotic disruptor, periodically throwing comets at Earth. Beckingham's model defines the companion as gravitational scaffolding. In this framework, the companion actively stabilizes the system on a 15.61 million-year resonance cycle. These 5 strict criteria will immediately falsify the entire mathematical model. The author invites rigorous scrutiny. If no Planet 9 is found, if the binary anchor is missing, if orbital simulations break the cadence, if the fragmentation signature is absent, or standard mechanics explain the ETNOs, the entire theoretical framework of the model immediately collapses. This framework interprets the outer darkness as the final, stabilizing pendulum of a deeply interconnected 1.7-year cosmic metronome.